Okay, everybody, today we're going to be talking about the compound interest formula. Uh, Last time that we met, before all this took off, we talked about compound interest, and people were working out compound interest sort of on a year-by-year basis. There is, of course, a formula that makes that a little bit easier, and we're going to go over that today. So, our compound interest formula is as follows. Equals p times 1 plus I to the n. Some of these we've seen before, others we haven't. I apologize for the focus. It's having a fun time today. That should get a little better as I write more down. So, A we've seen before. That is future value of investment or debt, depending on which we're talking about. P is the principal amount invested or borrowed. I we haven't seen before. I is the interest rate per compounding period. And I'll get more into that in a second. And N is the total number of compounding periods. Per term. Okay. So, a bit about this I, this interest rate per compounding period. So, as a quick example, let's say I've made an investment at 3% interest annually, but compounded monthly. So 3% interest compounded monthly. That's an H there, believe it or not. So, typically when you see an interest rate given, it is given in terms of a year. Wait for my focus to come in. Oh, this thing is doing great. I'll cheat a little bit. Usually takes that all right. So, 3% interest. So what this means is that in a year you're going to get 3% interest. But compounded monthly breaks that down a little bit differently. When it's compounded monthly, that 3% is broken up month to month to month. And then the interest you gain one month, you then earn interest on that the next month. So what this looks like in terms of our formula is our I value for this would end up being 3% stated as a decimal divided up into 12 groups because it's compounded monthly. And then that value is what you would use in your compound interest formula. Now we're going to do an example or two that's a little bit more detailed than that. So we'll start with an example out of your textbook. This is example 2 on page 22. Anyone having issues with your textbook, I would refer you to our Google Classroom site. There'll be a discussion on that there. So in example 2 on page 22, we've got Matt investing $23,000 in an account that earns 13.6% compounded semi-annually. The interest rate is fixed for 10 years, and Matt plans to use the money for a down payment on a house in 5 to 10 years. And what our purpose is in this example is to figure out how much money his investment is worth after 5 years and after 10 years. So, let's talk about 5 years in. So 5 years in, our future value is what we're looking for. The principal is $23,000. Our interest rate, our annual interest rate is 13.6%. We're going to use that a bit in a minute to figure out our I value. And this is compounded semi-annually. Remember how to spell annually. Doing good. So, for my I value, that tells me my I value is going to be 0.136, and semi-annually means every 6 months or twice a year. as opposed to biannually, which would be every 2 years. So compounded semi-annually means I'm going to divide by 2 when I find my I value. Now for my total number of terms, I'm doing this for 5 years, twice a year. So my 5 years is here, my semi-annually shows up in here. So in those 5 years, I end up going through 10 compounding periods. So, now that I know all this, I can use the compound interest formula to figure out the future value. It'll be 23,000 times 1 plus 0.136 divided by 2 raised to the power of 10. My trusty calculator can work that out, but just to make sure that we're all okay with working that out, put a little bit more light on the calculator for this. Got a little bit more. You can just put this all in as one. You'd have 23,000 times in brackets 1 plus, I'd put that interior fraction in brackets, 0.136 divided by 2, close both sets of brackets, and then raise that to the power of 10. And enter. So after 5 years, his investment is going to be worth $44,000, $44,405, I should say, and 87 cents. Rounding it to the nearest cent because it's a monetary amount. Now for 10 years in, my P and my R stay the same. And my I value will stay the same as well. The only thing that's going to change is my number of terms. My N now is going to be 10 times 2, or 20. I mean, I go through 20 semi-annual periods in those 10 years. So my compound interest formula will look very similar to above. The only difference being now that exponent is going to be 20 instead of 10. I'll work that out. Again, bring up the old handy dandy calculator. In fact, if I want to cheat, second entry will bring me back that last statement. I'll just go up here and make that a 2. And that's worth $85,733.96. And I can say that after 5 years, Matt would have $44,405.87 for a down payment. After 10 years, he would have $85,733.96. So that is the compound interest formula. I'm going to do one more example at a different term, and then I'm going to talk about. Ooh, pardon me. Don't worry, it's just a sneeze. I don't think I have COVID-19. 99.97% sure. Okay, so I worked with that example. I'm going to do one more example and then talk a little bit about a quick estimating method for this. Pardon my high-end technology here. So next we will look at example 3 on page 24. Here's focus again. Cheat a little bit here as well. Alright. So in this example, both Jolie, age 50, and her daughter Lena, age 18, plan to invest $1,500 in an account with an annual interest rate of 9% compounded monthly. If both women hold their investments until age 65, what will be the difference in the future value of their investments. That's the A part. I'm not going to do the B part because it's just repeating the same sort of thing. Okay, so this is the A part of the example. And if I look at both women involved, Jolie and Lena, in each case I want to know what the future amount is. In each case the principal is $1,500. In each case the investment rate is 9%, the annual rate. And in each case it is compounded monthly. So in each case my I value would be decimal 0.9 divided by 12. Where there will be a difference is in N. Jolie, I assume that's how we pronounce that, is age 50 and Lena is age 18. So, for Jolie's investment, she's going up to age 65, which means she will be investing for 15 years. So her N value will be 15 times 12. Whereas Lena, to get up to age 65, is going to be investing for 47 years. So she'll be investing for quite a bit longer. Seven times 12. 15 times 12 is 180. 47 times 12, I'm not going to do in my head. 564. Okay, so we've got a couple of compound interest statements to work out. So for Jolie, her future amount is going to be 1,500 times 1 plus decimal 0.9 over 12 to the 180. Times 1 plus 0.09 divided by 12, all raised to the power of 180. So that'll be worth $5,757.06. And I'd say the same for Lena, with the one difference that the exponent in her equation will be 564. And again, I'll use my handy statement here to just bring that last equation back, change this number to 564, and work out that, oh, she's doing much better. $101,461.71. And there you see the power of compound interest. At the end of their investments, their investment terms, Lena has, I just do a quick subtraction, $95,704.65 more. Of course, again, there's a time span of 32 years between when their investments come to term. But we see a bit of the power of compound interest. The longer that you can make an investment at, the more you'll get back, because you start earning money on the interest that you've earned and all that good sort of thing. Okay, that is everything that we're going to talk about today on using compound interest, although I'm going to mention one more thing that I said before. There's something out there called the Rule of 72, which is a way to estimate how long it will take for an investment to double, a compound interest investment to double. So that's called the Rule of 72. It is used to estimate the doubling time for an investment. And doubling time is, of course, just how long it takes for the investment amount to double, for the future value to be double what the principal was. And it is fairly straightforward. It takes approximately the rate as a percentage. Oop, there, I did that backwards already. 72 divided by the rate as a percentage years for a compound interest investment to double in value. And that's not exact, but it does give a pretty decent approximation. An example that follows this is example 5 from page 27, and I won't do both examples, but I will do one. And it describes Bert and Chris investing $5,000 by purchasing Canada Savings Bonds. Berta's Canada Savings Bond earns 8% compounded annually, while Chris's Canada Savings Bond earns 9% compounded annually. Estimate the doubling time for each. So, Berta's, it really doesn't matter how much her initial investment was, since her rate was 8%. Her doubling time will be 72 divided by 8, or 9 years. Similarly, Chris's rate is 9%, so doubling time will be 72 divided by 9, or 8 years. So the Rule of 72 is just a fairly simple, quick way to get an estimate for how long it takes an investment to double a compound interest. It's not exact, but it is pretty close. It works out pretty well each time. Okay, that's about all I have to say about compound interest for today. There'll be some suggested questions on the Google Classroom, and I hope this is helpful. If there's any questions or comments, actually make them in the Google Classroom site and not on YouTube. All right, thanks everybody.